as I mentioned, if this will be recorded, so if you want to go to Witten's seminar, I don't dare to stop you. But seriously, it's okay. It's totally fine. I think it's worth listening to Witten's lecture than my lecture. Okay, so. Still people here. Okay, let's get started. So black hole thermodynamics. So today I'm going to talk about the black hole thermodynamics. Okay, so when was that? Long time ago, we talked about the Kerr black hole. And then Kerr black hole, we have a Penrose process, something like a so R plus. Okay, and then so this is R0 is so here's the Auger sphere. And there's something like a so this rotating direction is like this way, and then we have the counter-rotating particle is entered, and then this is at the surface of the Auger sphere it become the static limit, and then if you have a particle, if it's analogous to E1 and E2. E2, in fact, E2 has a negative energy, but E2 has a negative energy, but the E1 has positive energy, so that the one can extract energy from Kerr black hole. And then total process is in fact given in the, so this would decrease both M and J angular momentum. Because I mean here the particle is first counter rotating. But it becomes co-rotating at the end. So the particle which comes out of the Kerr black hole co-rotating. Okay, co-rotating. And then co-rotating. So therefore, one can also extract the angular momentum J. Okay, both M and J. And total process is given by what we saw is this M is the kappa of 8 pi and del A plus omega H del J. So this way. Total process is given like this. So that's what we saw last by Penrose process, and so this is the one of the example of this black hole thermodynamics. And then so kappa is the so-called surface gravity. We already see gravity. And omega H is the one we so long time ago. Omega H is given by the angular momentum, Kramer dragging A over R plus square plus A square is equal to omega H. Okay. So that's what we saw for Kerr black hole. Yeah, and then so we would like show this one in more general setting. So we just use derive this how to say change of mass with area and the angular momentum by using Penrose process last time. but today I'm gonna derive it more generally. And in particular, so this, as I mentioned last time, is very similar to this one. dA, dE is equal to TdS minus PdV in thermodynamics, so first law of thermodynamics. Okay, first law of thermodynamics. And let us recall that the thermodynamics is the zeroth law, is the temperatures is the constant in equilibrium. And then first law is exactly this one. dE is equal to TdS minus PdV, like this way. And then second law is the entropy is the never decrease. And third law is it's impossible to reach t positive to t goes to 0 in the finite process, finite number. This is prohibited. This is prohibited. Is the finite number of process. Okay, so that's the thermodynamics, black hole thermodynamics. Sorry, so just usual thermodynamics. Okay, and then black hole thermodynamics, thermodynamics. What we are going to learn is the statement as follows. So this is surface gravity is constant at the horizon. So that's the horizon of the stationary black hole. And then here is the one, it's written here, there, dm is equal to kappa 8 pi dA plus omega h dj plus phi h d omega dq. Q is the charges of the black hole. And then the second law is the area law. And then here, the kappa, this is prohibited with the finite number process. Okay, so this is prohibited. So those are statements of black hole thermodynamics. And we are going to derive this one by step. Okay, fine. Okay, so let's to derive before derived like the zeroth law. First, let's derive zeroth law one by one. But before deriving zeroth law, so we're talking. We'll try to first see the property of this event horizon, and then So the property of the killing horizon. So these of killing horizon. Okay. Property of killing horizon. And then so number one is so at killing horizon, so what we saw is that the Raychaudhuri equation, we talk about that this expansion. Okay, so the theta is the expansion, this is the shear and rotation, is everything zero at the horizon, at the killing horizon. Killing horizon. So let's go killing horizon. So this is a property one. So this, as you recall, this is whatever expansion contraction. Theta is something like a contraction or expansion or dilatation, something like this one. And then this sigma is the shear, like this way. Okay, and then omega is the rotation. So this is sigma, theta, omega, rotation. And this is not this is all, they all vanish at the horizon. Okay, so to derive that, we recall the definition of theta, sigma, omega. So B mu nu is defined by the projection on the hypersurface. Beta, down alpha, k, beta, like this way. Sorry. So I should mention that the k is a fine parameter of the null geodesic. Is the null tangent vector of the King horizon, and its lambda is the affine parameter. Okay. So this is the definition. Sorry. So actually, B mu nu is the B mu nu is defined by the cone. So originally, so we just consider congruence. So we have a sigma, and the congruence of some geodesics, like this way. And then we just consider, in the case of the C, and the B mu nu is just a projection. Alpha C beta. So this is the definition of the B mu nu, and then trace of B is equal to theta, and then antisymmetric part is symmetric part is sigma, and the antisymmetric part is the omega mu. So those are the definition, as we recall. In the case of the so in this case it's really the k is a null. So this is the k is null vector. In the case of null, so we just define it. So as you recall, k is something like this way. It's a like, but we just define the opposite some other L, and the lambda is something like K is something like this one. Okay, and then you just define the hypersurface. So as you recall that so in the case of null, so there's no like a d minus 1 independent of orthogonal vector orthogonal to k. There's no only d minus 2 orthogonal vector except k itself. Because k itself is null, so the k itself is the orthogonal to itself. Okay. So therefore we just define the k and L are something like I already forgot. So this is 1, 1 and minus 1, 1. So it's something like 1 or something. And L squared is equal to 0. And then we define something like L, yeah, K, and then K dot L is equal to 0, like this. And then we define the metric, in this metric on here, H mu nu is something like G mu nu plus L mu K nu plus L nu K nu. So we define like this way, and then the rest of procedure is the same. So we just replace by the here is K. Okay, so that's how we define the in the case of null. So this the quantity that appear in the Raychaudhuri equation. So now we'll do the same thing. So it's hypersurface. In the case of hypersurface, hypersurface. Let's see. So here I can write. So there is no rotation. Rotation only appears as an initial condition. So we don't need to consider rotation. We can set omega to be 0 always for some hypersurface, or in the case of the null vector, so here is the codimension 2 surface. Codimension 2 surface. It's totally fine to define to set omega to be 0. So we don't need to consider this one. In the case of the really like a time-like geodesic or like a time-like geodesic congruence, so it can have an initial condition of omega. But for hypersurface, no need to think about it as an initial condition omega. So you can set omega to be 0. So therefore, so in the case of the omega equal to 0, when omega equal to 0, so you can just symmetrize this one, like this way. So that the B mu is always like, how to say, symmetric. You can set the B mu to be symmetric. Okay. Now we remember that the killing horizon is specified by C, which is the proportional to K. Okay, proportional to K. F is some function such that the C mu is equal to kappa C mu. So this is a proper normalization. So this is the Puro-Puriate normalization. Okay. Normalization. So that this is surface gravity. That's what we all learn. Gravity. And then we know that this C mu is a killing vector. So therefore, it satisfies this condition like this way. So this is a killing vector. Okay, and then we just plug that into here. So therefore, B mu nu is something like a H mu alpha, H nu beta, nabla, and another alpha. And F inverse C beta, like this way. So K is just a proportional to C. So therefore, you just multiply F inverse and apply this way. So now, if nabla acts on C, and if you symmetrize it, it's just 0 because of killing. This is killing vector. These are killing vector. And also, if nabla acts on F, it's just function. So it's just derivative. Derivative acts on F inverse and then C beta, and we know that C beta is transverse to C beta is proportional to K. So but it's transverse to this hyperplane, not hyperplane, codimension 2 surface here. So therefore, projection of this H mu alpha C alpha is always 0. Okay, if you use this one, this is equal to 0 always. So they use this killing vector property, and then this projection is equal to 0 because it's orthogonal. This B mu nu is always 0. So this means that B mu nu is 0 means that its trace also 0. Theta is trace of B. It's also 0. And the sigma is just a traceless part. How to say? B mu nu minus trace theta delta mu nu with appropriate normalization with some number. And both B mu nu and theta is equal to 0. So this is also 0. Okay. So those are the conditions. Okay. We need to impose So therefore, all the quantity of the Lechardt equation theta sigma omega equal to 0 at the Killing horizon. So if you use this property, one can just show that the property 2 is the R mu nu and C nu is equal to 0. So one can show this one. This is come from Lechardt equation. So let's recall that what the Lechardt equation is. The minus theta square over 2 minus sigma square plus omega square plus minus from the mu nu, k mu and k nu. That's what we saw. In the this is a no Lechardt equation. Lechardt equation. So Lechardt equation is very important in this classical theorem of the GR. So this 2 is really dimension of this surface sigma. This sigma. So in the case of the how to say time like this becomes 3. This becomes 3. But we know this is equal to 0, and this is equal to 0, and this is equal to 0. And if you restrict, sorry, this is the horizon. Sorry, if we restrict horizon, if you restrict the horizon, okay, horizon at the horizon it's always 0. Sigma is 0. So therefore, its derivative along the horizon is also 0. K is the derivative. K nabla is derivative with respect to this tangent vector. So therefore, it's always 0. So left hand side is equal to 0 at the horizon, and these 3 terms 0, and so therefore this is equal to 0. Okay, and we know that the k mu and then is proportional to f c mu. So therefore, R mu nu C nu is equal to 0. Okay. So this is a property 2 of the property 2. Any question at this moment? Okay. And then I explained this one like a long time ago, but to recall that, let's review what we have learned. So we have learned is that follows: the kappa square is equal to minus 1/2 nabla mu c nu nabla mu c nu at the horizon. So that's what we learned. Okay, that's what we learned. So let's derive that again. Okay. So if you use the Frobenius theorem, so this is c mu rho is equal to 0. So this is the property coming from Frobenius theorem at the horizon. It's coming from Frobenius theorem. Let's accept Frobenius theorem. Okay. So then we can use the Killing equation to obtain it from here. Is that the c mu rho c mu okay, so we can just write down the equation c mu c rho plus c mu sorry, rho mu plus c rho c, what was that? most likely I make a mistake. Okay, I hope I'm not gonna make a mistake. And then we just need to use the, okay, good. The property of the Killing equation to show that so this is equal to minus C nu down mu C rho. Okay, that's the property. So if you swap rho and mu, you should get the minus sign because of Killing equation. Okay, so therefore, so this is from here, one can just conclude that the C rho nabla mu C nu is equal to minus 2, and then C mu antisymmetric with nu and x 0. Okay, so that's the equation we obtain.
From the Frobenius theorem, you get the equation, right?
So Frobenius theorem, you can get this equation for Killing
from
for
that
us.
you get this last equation.
Yeah, this is equivalent to this one.
There should be 6 terms, right? If you
But overall constant is
There must be 6 terms.
wait. Sorry. So this means that the what was that?
3 terms with plus sign, 3 terms.
And the minus C mu nabla rho C nu like this way. Is that the case? Yeah, it seems like that's the case. Okay. Okay. Yeah, that's true. That's true. So in addition to that, we have some other term. Yeah. You're right. You're right. So in addition to that, we have the following term: C mu, C rho, C nu minus everything cyclic, C rho. C nu, nabla mu, C rho is equal to 0. That's true. That's true. Then, okay, that's true. I think it's the same. I think it's same procedure. I think we can just use the. Yeah, I think it's same procedure. Now I understand. So same procedure. So the lower part will give you. This is minus C rho, C mu, minus which one is the correct? Minus 2, yeah, it's correct. E mu and then, not mu and rho. Mu and then nabla rho, so not mu, is equal to C rho. So this part will give you this one, and the upper part will give you this one. C rho, nabla mu, actually plus, C nu minus 2, C mu and delta nu and x 0. I think that's the case. Is that the case? Right? And if you use a Killing equation, this one is equal to this one, right? So if you swap the indices, you get this one, right? So therefore, you should have a 2 here. 2 here, and this should be equal to this one. Actually, this one should be plus, actually, right? No? No, sorry. This should be plus. So we already knew that this is plus, right? And since it's anti-symmetric, right? And the minus sign, so this should be equal to this one. So therefore, this is equal to 4 is equal to 0. Okay? Okay, so then it's okay. It's okay. Okay, somehow I survived from your question. Okay. Fine. Then maybe then if you consider this equation 0 mu like this equation, okay, and then we just plug this one into here. Okay, anyway, so it's written there, so I can erase here. So minus 2 xi mu nabla nu xi rho xi nu, and then we know that this one is this one will give you kappa, so we can use this relation, so the definition of surface gravity, to get the minus 2 kappa xi nu nabla nu xi rho, and then the same thing happen, 2 kappa square xi rho. Okay? Therefore, we get the above statement. Above statement. That's what we did a long time ago. Okay. So with this preparation, one can show the zero slope surface zero slope. Okay, so the statement is zero slope, okay, zero slope. So this is the kappa is equal to constant, actually. Okay, so the statement is the surface gravity is, okay, zero slope, okay, kappa is equal to constant at entire killing horizon. H. Okay, so that's the zero slope. Let's prove that. Okay. So the killing vector will satisfy the following condition. This is I showed this one last time briefly. Is R nu mu rho sigma c sigma. So this one I showed last time. So you have to use the killing equation, of course. This can be derived by killing equation equal to 0, and also this first Bianchi identity is equal to 0. Okay, so if you use this one, one can show this one. So I think I explained briefly, right? R is R whatever. Sigma mu nu rho is xi sigma is equal to nabla mu nabla nu, and antisymmetric acts on like this way, okay? And you plug this one into this Bianchi identity, and use this killing equation a number of times, one can derive this one. So this one I already showed briefly last time. I don't know, last time or 2 classes or week before. But anyway, so this one, if you want to interested data derivation appendix 8.5, is written in the, if you want to, the derivation. So but let's accept this one at this moment and move on. So that's also same. So this one, Frobenius theorem is written in appendix B. The derivation of appendix B. I'm not going to derive everything. So if you derive it, it's going to be just boring, and then just takes too much time. Fine. And then what I'm going to do is what? So now, we just use the following thing. So C row, so index is somewhat strange in my lecture note, kappa square at the horizon edge. We consider this kind of quantity at the horizon, and we know that this kappa square is equal to this one. Okay, so therefore this one can be written as follows: minus C row sorry, like this. So the dou C is the, it's just a square. So this is just a dou C square. So if you act on the Leibniz rule, 2 cancel with 1 over 2, and you get this one. Okay, and then this one we already know, so we can use this identity to compute this quantity, and this is equal to I'm so stupid. Maybe I should write down like this way: mu, and then mu, and then I can directly use this quantity. So therefore, this is C row nabla mu C nu. Okay, and then R nu mu rho sigma C sigma. Okay, so that's what we have. Okay, at the horizon. So everything at the horizon. Everything at the horizon. And then we can just use the property of the Riemann tensor. So if rho and the sigma is swapped, Riemann curvature, Riemann curvature will be anti-symmetric. You get the minus sign. On the other hand, you have a rho and a sigma is symmetric because both are C, so therefore this should be 0. Okay. So that's we showed. Okay. Okay, so let's consider the following facts. So sorry. That's not what I wanted. So if you consider maximum extended Schwarzschild, like this way. So here is the killing horizon is all those these line. Killing horizon is also line. And then what we show is that it's a constant along. So K is something like this one. C is something like this direction. So what we show is that C is the, so along this derivative, kappa square is equal to 0. But recall that the so at each point of Penrose's diagram, this point stands for what in space-time? S2. S2, yes. So we don't strictly show that it's invariant under S2. It can, it's along this direction derivative is 0, but it can, vary along S2. It doesn't show. So from this derivation, it doesn't show that it's what was that? Doesn't show that this derivation doesn't show that it's how to say constant along this S2. So we need to show this one. So to show that we use this bifurcation. So bifurcation R sphere B. So we learned that C at the bifurcation point is equal to 0. That's what we should learn last time, long time ago. So we learned from linear space that this is B and this is U. And then, so the affine parameter, the K, K is always given by the small b, which is the, what was that, kappa b del b. No, I think this one, as far as we go. Capital B. No, what I'm doing? Sorry. I told you totally wrong thing. It's opposite. Sorry. Sorry. So this is delta V. Okay, delta V. Capital V. But killing vector we use is C, B, delta V, which is small b. Recall that b is related by small b by e to the kappa small b. And what was that constant? As far as I remember, it should be plus minus times kappa. This part I printed out. Yeah, yes, it's okay. This is something related to this one. I mean, strictly speaking, you can have a plus minus sign, but this is a relation between capital B and small b. And the metric is the du, dv, capital V, like this way. For in the case of the Rindler space, and then the capital B is the affine parameter. Okay. On the other hand, CV will vanish at this bifurcation point. So this is 0, and it becomes very small. This is C, and like this way, C, and it gets bigger and bigger. So this is the property of the C killing vector. Okay, so that's what we learned. So the alpha, and since it's proportional to V, okay, so here the capital B is in front. So therefore, at the bifurcation point, it should vanish. So that's what we learned a long time ago. At the Rindler space, we can use this fact to derive okay, so the bifurcation at B is actually two sphere. So therefore, one can just consider the tangent vector at the whatever point S. So tangent by S mu, something like a tangent by S mu. And we can just do the same computation. S rho kappa square at the bifurcation point is equal to nabla S rho C mu. And apply okay, the same identity. Okay. like this way. Same identity here, apply to here. But we know the C at the bifurcation point B is equal to 0, so therefore it has to be 0. Okay. So we know C at the bifurcation point is 0, so therefore this is 0. So therefore it's also along the surface it should be also 0. Okay, so this is a proof of the zeroth law of the thermodynamics. Any question on this one? Okay. But so we only need the example. We know all examples. So Schwarzschild, the rational non-stone, and what was that curve? The kappa is constant, right? Kappa is for Schwarzschild what? What was the value?
Over for n.
Good. For n. Okay. And unfortunately, rational non-stone, even I don't remember. It should be kappa plus minus, and it should be written r plus and r minus, and I forgot the value, so I cannot write that. It's written a note. I can write down the curve case because I wrote in somewhere in this lecture. Yeah. In the curve case, it should be something like this one: r plus minus minus r minus plus 2r plus minus square plus a square. Okay. So that's the case. And most likely, in the case of the rational non-stone, a is just replaced by q, capital Q. Okay. So the important thing is that so it's constant along everywhere in the case along everywhere. So that makes sense. And the important part is that so in the case of current rational non-stone, when r plus is equal to r minus happen, when does this happen?
Extreme.
Yeah, so in the case of extreme, m is equal to q or m is equal to a or something like that, then this will happen. In the case of extreme, kappa is 0. Okay. Kappa is always 0. So therefore the surface gravity is 0. So which means that the black hole temperature is equal to 0. Fine. Okay. Any question at this moment? So then, if not, we'll move on to first law. So we'll derive first law of the black hole thermodynamics. So now we consider small perturbation. So it's called this derivation. So we will just derive the two way. So first way is the so-called physical process. Okay. So physical process through a matter to a curved black hole. The second is the assume uniqueness theorem. Which states that the most generic stationary black hole is a Kerr-Newman black hole. Assume that then derive. First row, explicit calculation by explicit calculation. So I will do the both of them. Here, the one thing, the nice thing is the first process is one can derive first row by in general setting. But in the second row, we cannot here. If you can also. So this is the how to say neutral one. Therefore, this part I didn't write that dq. Phi h. This part it does not show up. No this time. No this time. So since the charge doesn't change, so there's no this time. But here we can do the explicit calculation. So the merit is you can do the explicit calculation and to see this first law. But the everything difficulty is just hidden in this uniqueness theorem. So uniqueness theorem, it just states that the stationary most generic stationary black hole solution is the Kerr-Newman. Black hole. And Q and G. Sometimes this uniqueness theorem is called no-head theorem. So we derive the two ways. Okay. Okay, so to derive that, so we just consider the following: we just characterize a matter which is thrown to the black hole, Kerr black hole, and then suppose it has so it has the momentum. So suppose it has the time direction is the u. Yeah, my notation is horrible actually. I don't know why I use J here. Okay, this is horrible notation. Yeah, I think I wrote somewhere in this J is not the angular momentum, but it's still confusing. I should use different letter. Okay, so this J is not good notation. What kind of symbol is better? I use J for current, but it's better to avoid it. What kind of notation would be better? J. Let's use maybe capital K. Okay, let's use capital K. K-A. Oh, okay, capital K. Capital K is minus P-A-E. U-P. So U is delta T. And then L is the angular momentum of the matter. MB, so MB is the del phi of B. Okay, so that's the actually. So this is kind of like a energy of this matter. So we just consider the curved black hole. Consider curved black hole again. You have Auger sphere R plus, and then physical process. So we just throw some whatever. Again, something thrown inside in a curved black hole. So which has the which is characterized by the energy momentum tensor TAB. And whose energy can be just measured by contracting with time, and whose angular momentum can be obtained by angular momentum vector is just contracting with the dou phi. Okay. Okay. And since we know that they both are so we know that both are, how to say, at the first order, I mean, since we've thrown away something, it's no longer stationary in entire space-time, actually. So therefore, these are actually not killing vector. If it is a stationary curved black hole, they are both killing vector, as we learned. But if we throw away the something, so it's no longer stationary in the entire physical process. But at the first order, these are the killing vector. Because if you assume car is very big, and the perturbation is very small, these quantities is very small, then we know that both are the killing vector. So therefore, at the first order, we can just assume that the Ka is equal to 0, the La is equal to 0 at the first order. Yeah. Perturbation. And the setting is exactly like this that we consider. So yeah, so we already knew that how the curve, the heterozygal curve space-time, but we just only look at the curve. I don't want to write down, but curve is something like this way. And then you have like this way. Like this way. So, but we just consider the following process, R plus. Which here is R plus, and we just consider these killing horizon H. Okay, killing horizon is really here. Okay, killing horizon here. And see how this perturbation affects the inner curve space-time. That's what we see. Okay, so this is a setting. So we use this affine like a, how to say, classical Zenkeres coordinate, capital B and capital U, and then we assume that around the horizon the square of H plus. So H plus is really this one. H plus is this part. We are focusing on this part. This physical horizon. H plus. So this H plus is characterized by U equal to 0. Capital U equal to 0. So the alpha metric is something like 2 du dv. I think minus is missing here. So there must be minus, right? I think Okay, so the coordinate is capital U, capital B, and yi and yj. So y1 and y2. I don't know y1 and y2. Kind of some kind of spherical coordinate. We assume. So therefore, okay. And then we consider the process of the if you just this matter is hit onto the horizon, what's going to happen? So therefore del m is given by minus of the horizon h plus. What's the difference between I call it this one somehow h plus is somehow this orange region. I call this only this region. I call this one somehow like an in my lecture note. Whichever, it's just notation. It's just notation. Okay, the way I wrote is very strange in that case. Anyway, so let's follow my lecture note and the Hodge star of k, and then the order j is the minus of Hodge star of l. So that's the how you change the black hole. But now we just consider around here. What's the volume element? So this direction is dv, like a kind of consider dv, and then around this point we have the two spheres. So therefore volume element is dy1, which dy2. So these are volume element of this horizon. So therefore Hodge star. So this is the one form. So this is the one vector, and if you take Hodge star to integral over n, what's important is Hodge star of k and b12. So since it's whatever, k can be understood in one form, and if you take Hodge star, you have a three form. And then three form, which can be integral over n, is the component of b and the y1 and y2. Okay, and then this can be understood as a square root h. And if you use the metric of this one, so volume element, total volume element is in fact square root h, du, which dv, which dy1, which dy2 is the volume element of this metric, where h is given in here. Okay, h is given here. Okay, so therefore this can be understood j. Just use the definition using a volume element like this way, u, and you can just use the metric to lower this one. So the pitch is something like a square root h jb, and this is equal to square root h k dot k mu. Oh, I'm sorry, not j. Sorry, my lecture not use j. K. Oh. Okay, small k. Okay, I have to be careful. K. Small k dot capital K. Okay. Small k is the affine parameter. This one. This one. Small k is this one. Okay, you have to be careful. So this k is really this vector. So therefore, if you contract with this guy, you just only pick this lower b, and the capital K is this energy vector. The same procedure you can do that. So therefore, in fact, this one is equal to. So this one is equal to minus n dv d square y square root h k dot capital K. Okay, and this is dv d square y square root h k dot l. Okay, so that's what we have from this computation of the Hodge star, and we need to evaluate this one. Okay. So the definition of capital K and L is given by contract with stress energy tensor T. So now we'll just plug that one into here and manipulate. Ah, oh my goodness, I'm so stupid. I want to keep this, okay. Okay. And then like this way. So this kind of process we are considering. Now, when we reach this point, we know that this the matter always have only like can take the vector something like let's see. It's actually like this way. So this is actually u plus omega h times m. So this is the vector. So what we learn is by frame tracking, the co-rotating particle becomes stationary at the surface of our sphere. I mean, stationary means the angular momentum becomes zero. It's not stationary, but angular momentum is zero at this point, and the co-rotating inside our sphere. At this point, it's forced to take this value, as we recall. Do you remember? So I wrote this kind of diagram. This is the r and the angular momentum of the vector, whatever I call it. Okay, anyway. I don't remember what I call it, J or something, L or whatever. L is this one, so I don't want to use this one. But anyway, so co-rotating something like this. So this is R a plus and R0, and the co-rotating, counter-rotating like this way, and counter-rotating, and it takes this kind of body. This kind of body, and this part is always at the horizon. At the horizon, this should be always u plus omega h times m. So this is the only body one can take. Ah, sorry, this is okay. So it's omega actually, omega h. Okay. So this is the only body one can take, in fact. So that's what we learn. So at this point, the vector will take this value. Okay. And this is indeed actually as I remember. This is actually nu. It becomes nu. So this guy becomes nu. So and this is CA. And we treat at the horizon. CA. Okay. So now I want to keep this one. So I will erase this one part. So this becomes killing vector. Okay, so now therefore, so delta m is given by n dv d square y, and plug this one into there, and then you can have a square root h tab kaub like this way. And the integral of n, and then it's the same thing, quantity appear here, and TAB, and the KA. So the K is small k. I should use small k. Small k. It's not capital one. This is CB minus omega H MB. Okay. Now we remember that CB is in fact equal to kappa times B times K, small k, right? Small k. I need to think about how I call it. It's capital K is not convenient. But anyway, so I'll change later. So we know that the K is a fine new vector, and this C is just a Killing vector that measure the surface gravity. They are related by kappa times V, so they are related by this condition. Okay, so therefore plugged out into here, then what we get is something like N and the same measure. So this is a measure, and TAB and KA, KB, and kappa times B. Okay, and minus omega H. And there's something same of N, and then square root H K dot L, small k dot L. Okay. So we already know that the TABM will give you capital L and then dot K. So that's what we get. Now we know the first time varnish. What was that? Okay, it's okay. Okay, so here you have to be careful. Yeah, the first time vanish only for stationary one. So not stationary. Oh, it's okay. It's okay. It's not. It doesn't vanish. Sorry. So therefore, so what we have is that the delta. I'm saying something stupid. Minus omega H del J. Okay. The second time is the omega H and del J. So this is what we have. Is equal to kappa over 8 pi of dV. I just do the dV, so dV, d square y, and then square root h times v, RAB, KA, and KB. Okay, so that's what we have. So here we use the fact that the Einstein equation, 8 pi TAB KA KB is equal to RAB KA and KB. Okay, so this is the Einstein equation for new one. So it's since K is the just nu vector, so we can ignore this g mu nu r part. So Einstein equation has whatever g mu nu GAB r part, but if you contract with K, since K is null, so this is gone. Okay, so therefore we can use this Einstein equation and plug into here, you get this one. For stationary, we showed that this is equal to 0. Stationary black hole, but now we throw something in, okay? So therefore, no longer it's stationary. So we cannot simply set this is equal to 0, okay? And just we need to show this quantity by perturbation. By perturbation, so the Raychaudhuri equation is become like this here. By perturbation theory is equal to minus R, AB, KA, and KB. At the horizon, at the first order, theta, sigma, and omega equal to 0 at the first order perturbation. Okay. But this is the really first order difference. So we have to use the Raychaudhuri equation. And then plugged out into here. Plugged out into here, and what you get is that the, I think instead of lambda, I should use this one as V. This quantity, okay, anyway, so delta M minus omega H delta J is equal to kappa over 8 pi, and then d square y, and then square root H V del theta del V and del V. Okay, that's what we have. And just do the integral part. Okay. And then what we need to do is just do the integral by parts. Okay. Integral by parts. Somehow I miss a minus sign. Somehow I miss a minus sign here. A minus sign here. And here what we get is just integral by parts. We have a kappa over 8 pi. And then d square y. And then square root H B theta 0 and infinity, and then what's that? Minus 0 and infinity square root H plus lambda dH dV dV. Okay. Theta dV. Okay, so that's what we have. Fine. Okay. Is everything okay? My derivation is okay. It should be okay, right? Fine. Is it okay? I hope I'm not mistake. I don't make a mistake. So it's okay, right? So this is dV. I just plug down into here and then just integral parts, you get this one. Okay, fine. Now, what's relevant is the I don't remember. So what's relevant is this guy. And the other term somehow you can ignore. How do you ignore? Oh, yeah. So the 0 and the infinity becomes stationary. So therefore, stationary black hole theta equal to 0. So this can be ignored. That's true. And then square root H is approach to finite limit at b goes to infinity. Somehow we can concentrate this one. Okay, let's accept that. And this one is equal to, in fact, if you use a Raychaudhuri equation, theta can be understood square root H and then d square root H dV. Okay. Okay. I think, yeah. The dV So yeah, square root. So therefore plug down into here, and what you get is that the kappa over 8 pi d square y, and then d square root h dv dv. Okay, and this is equal to kappa over 8 pi square root y square root h and delta h. This is equal to kappa over 8 pi and what you want, delta L. So that's the derivation. Somehow we only focus on this one. I have to mention why this is equal to, no need to consider. So this term is equal to 0 because I mean at the v equal to 0, v equal to infinity, it's stationary. Stationary black hole set equal to 0. So that's totally fine. And I think we can use the same reasoning for this one too. I think
V equals to 0 corresponds to the event horizon, right? Or
yes, yes.
okay.
So what we have looking at it, it's okay. Let's use analogy of the short shell, and then so you have like this way, but you just throw something inside. If you throw something inside, the black hole just becomes a little bit fatter, like this way. Become fatter. But v equal to 0 is correspond to this point. V equal to infinity correspond to here. 0, v equal to 0, v equal to infinity. Okay. But at this point it's stationary. So stationary black hole set equal to 0 at the event horizon. That's what I meant. And the third term, why we can ignore, is most likely it's second order. It's second order. I don't know, to be honest. Yeah, I think it's second order, because I mean, if you plug this way into here, it's a second order perturbation, right? D square root H square root V square, right? It's a second order perturbation, right? Is that the reason? Okay. If you accept this term is equal to 0, this term do not contribute. This term do not contribute, and this is a derivation of the first law of thermodynamics. So we just have this process to derive. So you just plug this into here, and then 1 over square root h cancel this one, and then if you integrate over this one, this will give you the how the area will change. So d square y del square root h will give you area, but it's del a, and so this is a derivation of the first law of Planck. Okay, let's take a break. I will think about why we can ignore this part during the break. How was the Witten's lecture? Does anybody? I think. Okay, let me think about why we can. Oh, seems like a seminar is over. Yeah, it seems like it's just all the. This is second order. So this is second order. So perturbation. So you don't need to include it. He hasn't come. Okay. Let's resume. So, in fact, this is the second order perturbation. In fact, this one. So this term is second order, because I mean, as you know, so that's theta is already first order perturbation, because I mean d square root h dv, and then d square root h dv is the also second first order perturbation. So therefore, if you multiply them together, you get the second order, so that you can ignore if you consider the small perturbation. That's the reason. Yeah. Any question around at this derivation on the? So I'll be brief about the second derivation. So in fact, so what you can show is the del m is equal to, I mean, just the explicit calculation. Del A plus omega h del j plus yh del q. So this one can be derived by Kerr black hole. I don't know Kerr Newman black hole. It's just an explicit calculation. I mean, just throw away all the computation mathematical. If you type correctly, you get the correct answer. I don't want to write down the Kerr metric. Okay, anyway, so the Kerr metric is parameterized ds squared is equal to I don't want to. Okay, anyway, so okay. It's written in the lecture notes. I don't think it's necessary to write down everything. Sigma d t squared And then the important part is the dt d phi is there, and then there's some big term, sigma is 2a sine square theta r square plus a square minus delta. And then you have some kind of radius, d phi square, and plus sigma over delta dr square plus sigma d theta square. Okay, so those are metric. Those are metric. I'm not gonna write down everything. So this part is I'm too lazy to write down. Sigma something like that. And then A is equal to angular momentum divided by m. Delta is given by r square minus 2mr plus a square plus q square. And then sigma is equal to r square plus a square cosine square theta. So important part is this q. So the difference is this part. This part from the Kerr-Newman Kerr to Kerr-Newman case. Okay. And also, so the gauge field is there. The gauge field is the A mu d x mu, and which is minus QR sigma dt minus a sine square sine square d phi. So these are all the field, metric field and the gauge field, and the horizon is given by m plus minus square root m square minus a square minus q square. So therefore extremum is m square is equal to a square plus q square. So that's the case. So this is the extremum. But usually it has to be something like this way. Extremum only when it's equality holds. Okay. And then we can just define all the quantity. So at the horizon. So omega h is minus gt phi, g phi phi. And this is A over R plus. I mean, just we already learned everything. Phi h is just minus A mu and C mu at the horizon. At the horizon plus, which is R. Minus A t plus omega h A phi, which is R plus Q. R plus square plus a square. Okay, and then kappa is given by r plus minus r minus divided by 2 r plus square plus a square. Okay, so those are all ingredients. Okay, those are all ingredients. And then area. Okay, area. I mean area, so I already told you how to compute the area. I mean, you just write down the hypersurface on the horizon, so the induced metric on the horizon, and then area is given by 4 pi r plus square plus a square. And then from there, one can just compute. I mean, it's just calculation. I plug all the quantity, and then they satisfy this following identity. Phi h q. They satisfy this identity. So this is just calculation. So plug everything, all formula written here, and then plug into here. They satisfy. The right hand side will give you m. It's a straightforward calculation. Okay. Okay. And then from here, one can just write down del A is given by R plus, del R plus, and the plus A del A, like this way, and which can be written as as follows: R plus square plus A square. It's just direct calculation. I mean, it's what's nice is you can do the explicit calculation to show this one. Like this way. Like this way. Okay, and then we notice that the this part is the same as this part, and then this part is the same as this part. Okay, and then in fact this is equal to R plus minus M, and then R plus square plus A square. So therefore, this is equal to omega H. This is equal to, what was that? Phi H. And this is equal to, notice that the 1 over kappa times something. Times, no need to multiply something. Yeah, that's it. And then, so therefore, what you get is that the E del M, actually it's written here. It's written here, but if you write down a bit more fancy way, it's become dH del S black hole plus omega H del J plus phi H del Q, where this is equal to kappa over 2 pi. Okay, and S is equal to A over 4. A over 4. A over 4. Okay, so that's the explicit derivation. I mean, you just need to do all the calculation by using quantity of Kerr-Newman, and then you can derive this formula. So this is the upper way is called small formula somehow. I don't know formula. Probably he first found it. Anyway. That's an explicit derivation. So this is super easy. Even like a diligent high school students can do that. But the important thing is, of course, derivation of Kerr metric, Kerr-Newman metric, and also the uniqueness theorem. So that if you assume this one, this is always true. So this is the if you assume this is the most generic stationary black hole. Now we move on to second law. Move to second law. Okay, second law. So this is called, famously called Hawking area theorem. Okay. Okay, so that to make a statement, I need to draw the figure. So you have a structure, like this way, and then so this is the called U inside of M. So this is the U is a so mg is the space time, and then here it's called with no energy condition. I don't think I use this new energy condition anywhere, to be honest. Okay, anyway, so let's make the things simple. And U is inside M such that the it's globally hyperbolic. Okay, so therefore inside a short shell, the global hyperbolic is only this region. Okay. So, and then because there's a Cauchy surface, you can take Cauchy surface, whatever. Cauchy surface is something like E, something like this, right? Cauchy surface. Yeah. Okay. So therefore, any how to say causal curve will around the U, the point in U, any causal curve should intersect with this Cauchy surface here. This is a Cauchy surface, sigma Cauchy. Okay, now and you just define a sigma 1 and sigma 2 like this way. So this is sigma 1 and sigma 2 like this way. And the intersection, we call it this, this is horizon. This is the horizon. And this intersection, I call it H1 and H2. So this point is H1 and H2. Okay, so that's a notation I use. Okay. Then, so the statement is that the area sigma 1 is less than or equal to area sigma 2. So that's the case. So that's the statement. Okay. Okay, so then, so we that's a Hawking area theorem, and we prove by using this the focusing theorem, and then so I have to remind you that the two facts. Okay, so, and then so the picture is as follows. Let's see. So this is H plus, and the Cauchy surface is something like this one. Cauchy surface is given by sigma 2, and then this is sigma 1. Okay, and then here is a horizon. So this part is a horizon. H1 and this is H2. Okay, and we just consider the null geodesic, something like this one. This is always like a, how to say, like this way. So that's a statement. So it never converges like this way. Okay. So that's the case. Okay, so here, so we just need to assume that so first let's show Sailor is greater than 0 on H plus. Okay. Okay. So let's show first this one. So to show that they show this one by contradiction. Okay. Suppose, okay, to show this by contradiction, suppose say is less than 0 at the H plus, okay. Okay. Suppose as at point P, okay. So suppose cell is at the point P. So then I think there is a point P. So okay. So this is on H plus, and a point P here. And by continuity, so you can just have the this any surface like some whatever horizon at a constant time, it should be set equal to 0 by continuity. And then, so we know that because of this focusing theorem, it tells us that the Sailor is the, what was that? Sailor plus tau over 2, right? We already showed this one, right? Tau over 2, or lambda in our case, lambda over 2. In the focusing theorem, Sailor 0 is here. If suppose Sailor 0 is negative, then by focusing theorem, there must be some focal point. Focal point will appear. That's what we already know. So everything on the high, this event horizon. Okay, but we know that. So if you have a how to say this is no geodesic or the no geodesic, but if there is a point here, focal point here, we already knew that from here, this point to this point, you can connect between. I mean, it's better not to write like this way. We can connect by time-like curve like this way. Okay, we already knew that we can just, if there is a new geodesic and if there is a focal point, after that there is some, how to say, some kind of like a shorter path, which is no longer known. Okay, that's we already showed. But I mean, as you recall, the Euclidean analog is a sphere, and north pole and south pole, whatever. Anyway, north pole and south pole, and if you just write down the geodesics, something like if you just go beyond, how to say, the south pole, starting from north pole, there must be always some shorter path, like this way, the opposite way. Because I mean, you can just always have, if there's since it's a focal point, you have, without changing the length, you can just move this geodesic to the other geodesic. There's a kink here, so that you can always like smooth out by shortening the length. Okay, shortening the length. The same reason. So if you have a focal point, after the focal point, there must be the time-like geodesic, time-like curve, which connects between these 2 points. Then this will violate this achronality of H plus. Okay. So actually, so H plus has to be achronal. So that's an assumption. So this is called, I think, strong predictability. Asymptotical predictability is space-time. Anyway, so this is assumption. H plus is diagonal. So therefore, this will bound. If you have a focal point at H plus, so this means that the it will bound diagonality. So therefore, theta has to be positive. Okay? Theta has to be positive. Theta is positive means it's really diverging. So therefore, area is always increasing. Graph argument is. So therefore, so to recall this theta is given 1 over square root H and square root H ddv or dd lambda, whatever. dd lambda is the affine parameter on the geodesics, which is always 0. So therefore, if you have a how to say, so if you have an H here and then H here, and it just there's always some, how to say, like a diverging geodesic is connected between H1 and H2. So therefore, it will tell you that the area of H2 should be greater than area of H1. Okay, because of this property. It's because of this property. So that's a rough argument of the Hawking area here. Okay. So that's the way of that. So we saw that the delta A has to be positive by Perron's process. So that's one example. But this is the way of proving in general cases. So the point is always this theta has to be non-negative. Okay, let's look at the example. So this is a proof, and then okay. So let's consider the following process. You have okay, I think most of people know, but it's better to explain something like this. So there is a long time ago, I think you guys are still not the Fudan, I think. So there is a LIGO. LIGO found a gravitational wave. So what's the source of this gravitational wave? So it's just a black hole collision. So there are two black hole. There's a two black hole, and then rotating each other like this way, whatever. And just binary black. It's called binary black hole. Black hole. M2. And eventually, just so. Since it's the same thing. So if you just have a charged particle, and if you move charged particle, it will generate the electromagnetic wave. So it's the same way. So if you just have a mass and it just move around, it just propagate the gravitational wave. So the gravitational wave is something like, roughly speaking, like this way. Like this way. It just form like this way. I mean, if you look at, so this is the frequency of how they move around. If you just go close to each other, frequency becomes really tiny, and at the margin it becomes really like a frequency becomes really big. So not the absolute value is really big. The margin will go around here, and after margin it just becomes stationary, and it becomes stationary curved black hole, so therefore there's no gravitational wave. So this is the really process of the really, you can see the really the binary black hole by looking at the gravitational wave. That's why it's kind of like a very magical. But once you have the black hole marginally, so you have an M3, and of course it's just rotating. So they themselves are rotating. Okay, rotating, and of course M3 should be less than M1 plus M2. Okay, so they has to be by energy conservation. It has to be, because I mean the binary system will propagate the gravitational, so they must lose that energy. Okay, so this has to be the case. Okay, so then we can consider the same process, even though there is no Schwarzschild black hole in reality. I'm not sure if there exists, but even if it exists, we cannot measure. We cannot observe a Schwarzschild black hole. Oh.
Does still the third law of thermodynamics apply for the system, like the area of whole system?
Yeah. Of course. Total area of the curved black hole. If you just compute this one, and it has to be if you compute the black hole of this one. So of course the angular momentum, you have to consider J1 and J2 and J3. Okay, and if you do the naive calculation, you just do the naive calculation. J3 is equal to J1 and plus J2, and then compute the area, so that the Hawking area will hold. But let me do this calculation. It's complicated, so let's do the simplified calculation. So 2m1, m2 is merged to m3, like this way. Well, in this case, both are Schwarzschild. Okay. So M3 suppose you have just no energy loss, okay? Then this has to be greater than square root M1 square plus M2 square, right? So this can be shown, right? This is true, right? Because we assume M1 and M2 are both positive. Okay, and this is equal to square root M1 square plus M2 square plus 2M1 M2, right? Right. This is equal to this one, right? Is it okay? But this has to be, so equality only holds when M1 either equal to 0 or M2 equal to 0 in the simplest setting. Okay? So therefore, there's no merging, which means there's no merging. Okay? This means. Fine. So when does this efficient is the most efficient? It means the efficient. The other is of course M3. So in the margin there must be energy loss, which means that the let's see. So these are energy loss. Okay. Suppose there is some like hypothetical collision. Spherical black hole, two spherical black holes somehow just merge and then become spherical black hole. There is no such a physical phenomena, but because I mean it's only merging will will create some no longer spherical symmetric and so on. So but suppose there is such a process occur. There must be energy loss is this one. Okay? Energy loss is this one. And let's make an estimate how much. Oh, sorry, it's opposite. Sorry, plus minus. Sorry. So this is the energy loss. You should point me out. So energy loss is efficiency. Let's consider efficiency m1 plus m2. This is coefficient, and this is equal to so this is the case. So it should be less than or equal 1 minus. Okay, like this way. And this becomes the most efficient when as you can easily imagine. So this is equal to 1 minus 1 plus m2 over m1 square, and 1 plus m2 over m1 square root, like this way. And you set this one is equal to x, and just plot it. Just plot it. And when does become the smallest value? But if this is smallest, this is the most efficient, right? So then of course when does become smallest value? This quantity. So this quantity becomes smallest when?
Maybe m1 is equals to m2.
Yes, great. m1 equal to m2 is the smallest. And then that will give you square root 2 over 2 minus 1. Okay. And this is the maximum efficient you can get from this collision. It's a really big number. And then those kind of like efficiency coming from black hole collision or black hole physics is really big. Okay. Any question at this moment? Okay, so then let me do the third law. Okay, third law. Okay, third law is that so stress energy tensor. So this is the by actually Israel, I think. Israel 86. So stress energy tensor. Okay. So if you assume the space-time or the matter satisfy the weak energy condition, so this is called weak energy condition. Okay. Then surface gravity of copper cannot be reduced to 0 by finite advance time. So this is the theorem. Oops. So instead of giving so kappa equal to 0 when? When does kappa equal to 0? Yeah, so this become extremal. So this means that in the case of curved black hole, so just throwing away lots of like how to say the particle which has the angular momentum, whatever core, so core black hole, and then rotating, and just core rotating particle. If you put lots of like whatever matter which has angular momentum, and to try to increase the angular momentum of black hole itself, okay, but it cannot reach this extreme by finite amount of process. That's what it means. So the same thing happened in for whatever. Rystad Nordstrom, but Rystad Nordstrom is physical black hole, but the car black hole is the physical. So this means that even if you put a lot of matter in the angular momentum, you cannot reach to the extreme. So therefore, theoretically, so that's what it means. Instead of general proof, I just give you some example, of the rational Nordstrom case. So rational Nordstrom case, when m is equal to q, it becomes the extremum. But we try to show that this will never occur by just solving some. By using this weak energy condition. So the important part is this weak energy condition. So important part of this theorem is this. So we have to assume this weak energy condition. So let's consider rational Nordstrom black hole and throw incoming, ingoing. How to say, no fluid, charged fluid, ingoing charged, no fluid, Okay, so let's consider something like this one, and then rational Nordstrom. Sorry, I think I wrote something strange. Penrose diagram for car. The one I wrote is the car. Sorry. Anyway, so. Okay, let's set then the car. So this is actually it's a rational Nordstrom. Yeah. Like this way? So this is car. Actually, no, sorry. This is rational Nordstrom. For car, you need to add this one. For car, for maximum extended. Sorry. The last time that I wrote it, but that's not important. Rational Nordstrom. And again, we consider this part. Important part is this one, because it's physical. So this, I call it this H plus. And then I just throw some charged new one. So I just throw this one into some charged fluid from I minus, I plus, okay. I plus. And this kind of like a think the experiment, how to say, Gedanken experiment of first done by Baidia. So Baidia in, I think, 1950 something, around 50 something. 50 something. So it's called something called Baidia metric. So he considered the following thing. So he considers the ingoing Eddington-Finkelstein metric. And if he perturbs as follows. So the mass of the black hole depends on the B. So they recall the okay, so this one is B is constant. B is constant, right? Am I doing something stupid? No, yeah, this should be B constant. What am I doing here? I should use U instead of B. Sorry, what's the ingoing? It should be B, right? Sorry. No, it's okay. So what was the Einstein? So this is R equal to 0. So this is Eddington. So this is R equal to 2m. 2m Eddington Finkelstein ingoing is always like this one, right? This is B's constant surface, right? B is constant, right? Yes. Yeah. And then R is constant surface is always something like like this way. I don't remember the detail, like this way. R is constant surface is something like E. Yeah, it should be okay, right? It should be okay, right? Yeah, it should be okay. So this is R equal to 2m, and then right hand is something like this one, right? Does anybody, am I correct? You guys, I wrote this figure like a long time ago. I don't remember. Okay, anyway, so this is the case. And you just consider this kind of stuff. Okay. So here is B is equal to B0. Okay, B equal to B0, and since we just put the something around here, so B is less than B0. It's just original how to say? Original rational non-storm metric. But if you put the charge metric, charge matter, no matter. So here it's like a step function. So the matter and so on is something like the original body is M and B, and B0 is here. So it's the original body, but after this one, it's like a Heaviside function. If you put this one, so this is B is constant, right?
Yeah, it is.
Yeah, B is constant, right? So therefore, so around this region it's original, but if you go here, the black hole knew something like they absorbed this charged fluid, so that there is some change will occur. So the same thing happened in Q, like this one. So this is the Gedanken experiment that Beide did. Unfortunately, I don't have so much time, so therefore it depends on M, it depends on B. Now, M and Q depends on B. Okay. Sorry, I think this diagram. Sorry, I think I have to correct it. This is not R. So R equal to 0 and R equal to 2m, and I wrote like so this is B. Okay, this is B, and then the one I wrote is U actually. U. These are U. It has to be U. Okay, because it's right cone. So these are U's constant. So this is B constant. And this U is constant. Sorry. This one I have to correct it. So it's not R equal to constant. Sorry. Unfortunately, I don't have a time. So if you just need to solve this Einstein equation by using this one, and then so the R. So let's call G mu nu is equal to R mu nu minus 1/2 G mu nu R. So let's assume this one. Then GBV is the original one, GBV of 0 plus 1 R squared So this guy is the original rational. This is the original Einstein tensor. Rational non-symmetric. You can just compute this one by using the original one. But detail is not important. So the important thing is that since we just assume that now M and Q are depends on B. So therefore, there is a derivative term will affect sometimes this stress energy tensor. Okay. If it is a heaviside function like this way, this is a delta function at the B. So if it is like this way, M and Q are like this way, this is the delta B minus B0 with some number. But anyway, so that's what we get. So therefore, so here to solve this equation, so we need to assume that T mu nu is the original T mu nu electromagnetic plus T mu nu dust or no fluid, we call it fluid, like this. So this is the original one that we assume for rational snowstorm, and then T mu nu is the fluid. We throw into the black hole. So that's the case. Then T mu nu fluid is something like a rho L nu, where L is given by minus alpha mu B. Okay, so and rho is equal to this guy. And then times 1/8 pi. You have to multiply by Einstein equation. So this times 1/8 pi is equal to rho. Okay. L mu is just vector. This vector. I think I'm no, opposite. So L mu is something like it's a gradient, right? Gradient vector. So it should be something like this. This is L mu. It's orthogonal. It's a gradient vector like this. Okay. Okay, and then we just need to solve the equation, Einstein equation. Okay. Okay, so therefore, so what we need to do is and the T mu nu electromagnetic is the P minus 1, 1, and 1. P is something like Q square B times 8 pi R to the 4th. Okay, so that's the case. So that's we already derived long time ago. So it has to be, so the T mu nu has for electromagnetic should be traceless. Okay, So therefore minus 1, 1, 1 is become traceless. And P is the just a value of this this GBV0. GBV0. It's just value of GBV0. Okay. Then, so if you assume the weak energy condition, U mu, like this way, is greater than 0, will tell you that this one, and plug this guy into here, what you get is that the rho dV d tau square plus P. So that's what you get. Okay, it has to be greater than 0. Okay. So therefore, so the weak energy condition means that this guy, rho, has to be greater than 0. So since this is positive, and then and this is positive, okay, and rho is given by this value, and so therefore weak energy condition. So this can be arbitrarily large. This can be arbitrarily large. Arbitrarily large. So therefore, this has to be positive. If it is negative, this quantity dominates. It can be negative. So this means that the rho has to be greater than 0. Okay. Okay. And then we just consider the following things. So the 4 pi r. So energy field inside a black hole is given by like this way, rho plus, and then which is given by m dot minus q and q dot plus square root m square minus q square times m dot. Okay. Since rho is positive, this has to be greater than 0. It has to be positive. So I just plug rho in here. So rho is this value, and r plus is, as you know, r plus is the m plus square root m square minus q square. Okay, so that's what I used. Okay, and then just plug it, plug this quantity for rho into here. You get this. Okay, suppose. Okay, let's not erase that. Oh gosh. Suppose finite advanced time, so this m b0 is equal to q b0, with b0 is a finite time. And plug that into here. What you get is that the 4 pi r plus cube rho r plus, let me finish, is the m dot minus q dot, okay, at the point b0. Okay, maybe 0, and this has to be greater than 0. This has to be positive. Okay. So I just plug the m is equal to q in. So then this term vanish. M is equal to q. This term vanish, and q is equal to m. So that what's left is m times m dot minus q dot. Dot is derivative with respect to v. Okay. So this is positive, but now we assume that this is the extrema, or the extrema. So this already cannot be positive. M is positive, but this means that the m minus dot q dot is positive. So therefore, it goes beyond the extrema. So unphysical. So this means that okay. So therefore, delta minus has to 0. So therefore, this contradicts the extremality of the black hole. So therefore, this means that the contradiction. So therefore, you cannot achieve this one with the finite amount of time. So that's one way to derive. Is the yeah. So wrong. Okay, let's finish at this moment, and then from next week we'll go into this QFT on curved spacetime. Okay. Okay. Thanks for coming.